Hey there, this is Mrs. Sharp here with some more information on types of half-life problems. So in our type A problems, the keywords we were looking for was how much is left that's still radioactive or how many atoms are still radioactive. We were looking for some kind of an amount of our sample. In type B problems, we want to know how old the sample is or how long that sample has been around. So those are the keywords you are looking for in type B problems, which will be questions 3, 4, and 5 on your practice problems. And this is what they use for carbon dating. So if we're trying to figure out how old like a wrap from a mummy is or a dinosaur bone or something like that, these are the types of calculations that scientists do. So it's kind of cool. All right, so let's talk about the steps that you're going to use. So here's my example. A 57.00 gram sample of radon contains only 7.125 grams of its original radioactive atoms. Then how old is that sample? So I want to show you the equation that we ended up with for our type A problems, and we're going to work backwards. Okay, so we said that the amount left that's still radioactive, or N, is equal to the amount that we started out as radioactive at time 0. And we're going to multiply that by 1/2 to the power of N. Okay, now just as a reminder, we're going to go back and we're going to just define these. I don't know that all of you have this in your notes anyways, and if you do, this is a good spot to double check that you do. So N is how much is radioactive. N0 is how much was radioactive at time 0, so originally. 1/2 is just the definition of half-life, so we need to just keep that in there. And then N is the number of half-lives that have passed. Sorry, my handwriting is terrible. Okay, so we know big N, that's red, how much is radioactive? N0, how much was radioactive originally at time 0? That blue 1/2, or 0.5, is the definition of half-life. So how many times, we need to divide that in half. And then N is the number of half-lives that have passed. So can you guess which variable we are going to be solving for in these problems? Think about it. So we want to know how old the sample is. So the only thing in here that's time is this little n here, the number of half-lives, because we know a half-life is measured in some kind of a time interval. All those half-lives were seconds or days or years or microseconds. So that is what we will be solving for. So in this case, what do we know here? We know that we had 57 grams of radon that contains only 7.125 of its original radioactive atoms. So it looks like we know N and N0. So 57.00, it looks like, is what we had to start with. And that makes sense because it's bigger than 7.125. So it's decayed. It contains only that much. So it's decayed down to 7.125 of its original atoms. So how old is it? So what we're going to do is erase. I'm going to erase these definitions here. And let's see. We'll plug in some numbers and put it into our calculator and see what happens. So we know N and N0. I really thought this was going to be faster. I apologize. All right, so N is 57.00 grams, and N0 is 7. Oh, excuse me, I already messed up. N is 7.125 grams, because that's how much is still radioactive. And 57.00 grams is how much was originally radioactive. So we're going to keep our 1/2. And then we're interested in knowing how many half-lives have passed. So our variable is n. So what we're going to do is right off the bat, we're going to divide each side, in this case by 57. And what that's going to do for us is get the 1/2 n part all by itself. Okay, I got 0.125 grams canceled, and it looks like I have 4 sig figs in each value, and right now I only have 3 written down because the 0 at the beginning doesn't count. So I'm just going to add in another sig fig there, and that equals 1/2 to the n power. So this is where it gets tricky. If you want to solve for something that's an exponent, we have to use a logarithm. And so that's really easy. That's easier than it sounds. So what we have to do is on the right-hand side, we're going to bring that n out front. N times log of 1/2. And then because we took the log of 1/2, we have to do the same thing to the left-hand side. So it will be log of 0.1250. So what we're going to do is we're going to punch in our calculator log of 0.1250 and get an answer. And then we're going to do the same thing to 1/2. And I'm going to write those over here. Okay, so for those of you using your iPad or your phone calculator, to put that in, like for this first one, the log of 0.125, you're going to actually punch in 0.125, and then you want to find the button that says log subscript 10. So if you put in 0.125 and hit log subscript 10, you should get negative 0.9031. So I use 4 sig figs again. And on the other side, we got to keep n, and that's going to be times the log of 0.5. So again, you're going to put in 0.5 and then hit your log base 10, or it's log little lower subscript 10, and you'll get negative 0.3010. Okay, so then solving for n, we're just going to divide each side to get n by itself. We're going to divide each side by the negative 0.3010. So I'm keeping 4 sig figs there. And when I do that, I get n equals 3.000. So remember what n means. That's the number of half-lives that have gone by. So this sample is 3 half-lives in based on the numbers that we've calculated. And actually, for this one, since the numbers come out like super clean, check this out. So we start with 57. If I divide 57 in half, I am going to get, let's see, 60 would be 30, so 28.5. Is that right? 28.5, 26, yeah. So 57 divided in half would be 28.5. Then if I divide 28.5 in half again, I would get 14.25. And then if I divide 14.25 in half, I would get 7.125. So if I would have just divided 57 in half until I got to 7.125, I would have known that 1, 2, 3 half-lives had gone by. But it's not always going to come out nice and clean exactly like that. Like a lot of times it'll be like a random like 1.78 half-lives have gone by, and then this up here fails us. So that's why this algebra part down here is good to know, because if it's not this nice whole number of half-lives that have gone by, we can still figure it out. My point is that half-lives does not really tell us how old. It's telling us how many half-lives have gone by, but we need to know like what that is in a unit of time. So we need to know like what is the half-life of this particular isotope. So I'm assuming in this question that this radon is radon 222, so you could just Google that. So I'm going to Google it right now. Half-life of Radon 222. Okay, for Radon 222, I got that the half-life is 3.8 days. So again, I just looked it up. And we know that 3 half-lives have passed. So we need to multiply 3.00 half-lives. And basically what we're doing is this. We're saying there's 3 half-lives. Let me get this. And there are 3.8 days per 1 half-life. So that's why we multiply. So we know 3 half-lives and each one is 3.8 days. So altogether that would be, let's see, 3 times 3 is 9 plus 11.4. And look at our sig figs. I've actually got 4 here and only 2 here. So my answer should only have 2 sig figs. So really, it comes out to be 11.4 days, but rounded to the nearest 2 sig figs, that would be 11 days. So it's 11 days old. So that's how we do it. So I want you to try some type B questions now on your practice problems. Get those done and turn them in. Thank you.